We've talked about derivatives, and now we need to know how to write them down, what the notation is, and we'll be able to use that notation to help us make models. So let me remind you of what we've done. We've defined the derivative as this f prime of x, its limit for h near 0 of a fraction. Bottom of the fraction is h, that's the change in x, it's the horizontal distance, and the top is the change in y. And this does three things. It's the derivative, it's the instantaneous rate of change, and if we're talking about positions, that makes it the velocity, and it's also the slope of the tangent to the graph of the function f. And so going back and forth between these three is what helps us use the derivative to do interesting stuff. So how do you write it down? Well, I've already said it's f prime. The issue here is this. F prime is a function, so it has a derivative, and so its derivative is, now the logical thing would be to do something like this, is to say f prime prime. So there's a function, and then you put it in parentheses to kind of glue it all together, and then you take the derivative. The notation for this is f prime prime. Well, no one says it that way. It's f double prime, and that's a very common way of talking about it. So that's the second derivative. And then there's a third derivative, and there's a fourth derivative, and in some applications you go on taking derivatives until you run out of energy or your mom calls you in for dinner. So now the thing is that in the situation where f is a passive function, the derivative is impossible to know. That's why it's important to write it down. And so because what we can do a lot of times, even if the function is passive, lab data or something that's passive, we might be able to get someplace with properties of the derivative, and as we go through the course, we'll find ways to use those properties. This is a big deal. Use those properties to find out what the function is. So that's the prime notation. It's got strengths and weaknesses. I find I use whatever is most convenient at the moment. So there's another notation, and this is due to Leibniz, and I'm probably spelling Leibniz incorrectly. You never know. Leibniz was the co-inventor of calculus. Leibniz was on the continent, Newton was in England, and they invented it about the same time. And what Leibniz wrote was, well, y equals f of x. There are three different ways that you can use this Leibniz notation. And so one way that you can do it is to say the derivative is dy by dx, not dy over dx, it's by dx. And so that is a very useful thing because it tells you what the variable is. You'll see why this is important in a minute or two. Sometimes you might write df by dx, and that's because y is equal to f of x. That's the same thing. And sometimes you write d by dx, nothing on top, and I'm just going to put this in words of the formula. So those are three ways that you can do this. So that's d by dx of the formula. And so, for example, d by dx of x squared minus x is 2x minus 1. This is something you read about, we haven't talked about. So I'm going to take the derivative of the function whose formula is this. And so I just write the formula instead of introducing another name and more confusion. Okay. The second derivative, forget what it would be logically. It is the following. It still looks like a fraction, but it's a by. And the top is d2y, not d squared, d2y by dx squared, not d2, not x2, x squared, d2y dx squared, that's second derivative. And the third derivative is d3y by dx squared. And what you're seeing here, the reason that this works out is that you're taking d by dx, that's the derivative, and like I said, you can take the derivative of a formula. So in this case, you're taking the derivative of dy by dx, and if you ignore the parentheses, you've got d dx, that's like d squared, but it's not d squared, it's d2. And then you have dx dx, that's like dx in parentheses squared, but nobody writes the parentheses. So d2y dx squared. Okay, so let me give you kind of it's a little bit of a made up situation, but not so outrageous. So you've got a bug on a hot plate or on a hot wire, and the temperature of the wire varies. So so let's let the temperature be H. So that's the temperature at position S. So H is a function of S. I'm using H because T is kind of a bad letter because we're going to have time here. And so, so there it is. Let's let T be time. And because the bug is moving around, I guess it's just moving along the line, different times it's at different, sometimes it goes backwards, places. And so you have a coordinate S for every particular time. That may be a passive function, that may be an active function, but S is a function of T. But wait a second. H is a function of position. It's hot over here, and it's cooler over here, hot over here, cooler over here, or something. So the H is say decreasing as you move along. So there's a composition here. You take T, and you find the position, that's S, and then once you have S, you can find the temperature, that's H. Or you can bundle these all together as a composition and say, well, at any particular time, the temperature is this. So H is a function of time alone. So we've got all these derivatives, these rate of change of H with respect to S. That's how H changes with position. We've got rate of change of H with respect to T. That's how H changes with respect to time. If the bug is moving fast, H is going to move fast. If the bug is moving slow, H is going to move slow. If the bug is moving backwards, H is going to go backwards. And we also have ds by dt. So what we would like to know is, so we've got dH by ds. That's the rate of change. I'm abbreviating that with respect to position. And we've got ds by dt. That's the rate of change. I'm abbreviating that with respect to, I'm abbreviating that, time. So these are very standard notations, and ROC, rate of change, with respect to WRT. And the fancy Subaru is WRX. It's closely related, but not that bad. And then what we would like to know is the rate of change of the temperature H with respect to time. And we can just write that down. That's the thing with this notation. You can just say, oh, I have a notation for the rate of change, and so I'm going to write that down. That's dH by dt. So that's the rate of change of temperature with respect to time. And now I'm going to show you something that is one of the most important things in calculus. How does that derivative of a composition, T goes to S, S goes to H, that's a composition. How does the derivative of that composition work? And it is really remarkable. It is dH by ds, that's one of the rates that we know, times ds by dt. So luckily these aren't fractions, so well, they sure look like fractions. So you're not going to cancel. Well, it sure looks like you're canceling, but this tells us how the derivative of a composition works out. If there are 2 scoops of raisins in a package of Kellogg's Raisin Bran, and there are 12 packages of Kellogg's Raisin Bran in a carton, there are 12 times 2 scoops of raisins per carton. So this is a big deal. This is the chain rule, which we use over and over again. And we don't have to know what the functions are. In fact, sometimes we can use this to find what the functions are, but we know how the derivatives are related, And that's what's going to be able for us to make models. One final note, worth saying again, that ds by dt, so s was position and t was time, ds by dt has a special name. That's the velocity, rate of change of position with respect to time. That's velocity. Velocity has a sign. It can be moving in the positive direction or the negative direction. I guess I did that backwards, sorry. And so velocity has a sign. Its rate of change, that's d2s dt squared, that's how they say it, is the acceleration. And these two right here are the basis for all of the models of dynamics that people do. Okay, so definition of the derivative, the three things it does, the prime notation, the Leibniz notation, and the chain rule. The chain rule, that's the big important deal here. So here's the notation. This is also in the Hughes Hallett book or in my book or whatever, but it's fun to talk about. Well, I think it's fun to talk about. So talk to you soon.